In this video, I would like to show you how to find the resultant when 3 or more vectors are present. You already know how to do this graphically, and this tutorial will show you how to do it using algebra. To review, graphically, you simply place all the vectors head to tails. So I have these vectors A, B, and C, and if I use the head to tail method, I can take vector B and move it so that its tail sits on the head of vector A, and now I can move vector C and place it head to tail with vector B, and then the resultant connects the beginning or the tail of vector A to the head of vector C. In other words, the beginning to the end, and you have it right there. So if we were to solve this graphically, you would see the resultant is the purple vector located as shown. To find the resultant algebraically, we need to first find the x and y components of each vector. So the x component of vector A is right here, and the y component of vector A is over here. And likewise, the x component of vector B is located here, y component over here. Notice that there is no y component for vector C. Vector C lies entirely on the negative x-axis. So that is the value we'll be using when it comes time to use it. Let's take a closer look at what we actually do with all of these components. We'll be adding up all the vectors in the x coordinate and also adding up all the vectors that are on the y coordinate, and we'll use these vectors to determine the resultant. So to make this look a little bit easier, let me take away the original vector A and vector B, and we're just going to work with the components. So we're going to find the sum of all the vectors in the x direction. So that would be the x component of vector A and the x component of vector B. Remember, this would be done head to tail. And then vector C lies entirely on the x-axis, and that's in a negative direction, so we have to subtract that. And so the sum of these three vectors is going to be just this distance and direction here, indicated by the purple arrow. Now let's add up all the vectors acting in the y direction. Let's take the y component of vector A, and the y component of vector B is negative, so that has to be subtracted. So let's go ahead and show that being subtracted. So the sum of these two vectors then is this little vector here, as shown. These two vectors are the legs of a right triangle that define the resultant. Let me show you. Let me take the sum of all the x's, put it back on the x-axis. Let me take the sum of the y's and put it momentarily on the y-axis. But to show that it forms a right triangle, I'm going to go ahead and make it head to tail. Just move it over here at the end of the x-axis. And so our resultant is actually this vector right here. And now you can use the Pythagorean theorem to find the actual value, the magnitude of that vector, and then we'll be using the tangent function to find its precise direction. Now I can go back to the previous slide, and so you can see that we get the same resultant using either method. I did it graphically here using the head to tail method, and I actually did it graphically on this page using the sum of the vectors in the x direction, the x components, and the sum of the y components to define the resultant. Let's go ahead and use actual numbers now. Here's the coordinate plane, and I like to set this up using a tabular format where I list the vectors A, B, C across the top, and then I go across adding all the vectors that are acting in the x and y direction. Now these are the vector components that I showed you on the previous slide. So let's get the values now, and you see the x component of vector A is 80 cosine 65. You can see the vector flashing as well as the value. The x component of vector B is 100 cosine 20. And the x component of vector C is vector C, and that is a negative value, so that is subtracted. Now, if you're not comfortable with your trigonometry where you can come up with these values as I have right across the top, don't get stressed out. I'll show you on the next page where you can calculate these values off to the side and then plug them into this table, and it will look just like this row here, where I've done the calculations. The sum of the x components is equal to 33.8 plus 94 minus 60. That gives us a value of 67.8. And we'll do the same thing for the y components now. The y component of vector A is 80 sine 65. The y component of vector B is in a negative direction, so that has to be subtracted. So it's the negative of 100 sine 20. Vector C does not have a y component at all, so that is 0. We put these values into the calculator, and we come up with 72.5 plus negative 34.2 plus 0 is 38.3. Now you can see what this looks like down here. So the sum of the x components, 67.8, can be represented by the vector here. And the value for the sum of the y components can be represented by this vector, purple one here. And these should look familiar, as we already had these drawn on the previous slide. Now I'm going to pick this up, the y, sum of the y's, and you can see our y component. That's our two legs of a right triangle. So we can then define the resultant by using a Pythagorean theorem. And we'll take the square root of our sum of the x's squared plus the sum of the y squared. And we get a value of 77.9 for the resultant. And let me click on it, and you can see that value, what the vector looks like, and what the value is. To find the direction, we have to use the tangent function. Let me pull this out. So the tangent of the angle, and we're talking about the angle between the x-axis and the resultant. The tangent of that angle is equal to opposite over adjacent. You can see that the opposite side is our value for the sum of the y components. That is 38.3. The adjacent side is our value for the sum of the x components, 67.8. We take the inverse tan of that ratio, 38.3 divided by 67.8, and we get a value of 29.5 degrees. Your answer then would be that the resultant R is equal to 77.9 at 29.5 degrees north of east, or you might say 29.5 degrees above the positive x-axis. Remember, vectors include magnitude and direction. Now, if you're uncomfortable with the sines and cosines, let me show you another way that you could set this up. Here we go. Here are the original three vectors and the components. And what I suggest is off to the side, and let me remove this covering here. Off to the side, you can calculate the components. So you can see the x component for vector A is defined by the cosine of the 65-degree angle. So the cosine of that 65-degree angle is equal to adjacent over hypotenuse. Now the adjacent side is the x component of vector A. So I write that as a sub x. And the hypotenuse is the vector itself, which is 80. So you can see how the x component of vector A sub x, is then equal to 80 cosine 65, and that's 33.8. And you can see on this earlier slide that the x component of vector A is 80 cosine 65. Now let's go back. Let's look at the x component of vector B, and we'll find that that is defined by cosine of 20 degrees, and that's equal to, again, the adjacent leg, which is the x component of vector B, divided by the hypotenuse, which is 100. So B sub x is then equal to 100 cosine 20, which is 94.0. Now the 100 cosine 20 is the value that we put in on the previous slide, right here. Here's the 80 cosine 65, and the x component of vector B is the 100 cosine 20. So that's where those values came from if you were puzzled by that. So you do that for the x components of vectors A and B, and then you can go ahead and make your tables, columns A, B, and C, and the sum of the x's is equal to your calculated value of 33.8 plus 94, and don't forget vector C, that's negative 60, and you get 67.8. You can do the same thing for the y component vectors, and if you look at the y component of vector A sub y, you'll see that that is defined sine 65 is equal to the opposite leg over the hypotenuse. The opposite leg is the y component of vector A. So solving for that, you get a sub y is equal to 80 sine 65, 72.5. Doing the same thing for the y component of vector B, you get b sub y is equal to 100 sine 20, and that's equal to 34.2, and you stick a negative sign on that because it's in the negative direction. So then you write out that expression here. The sum of the y components is equal to 72.5 plus a negative 34.2 plus 0 for vector C is 38.3. Then go ahead and solve it just like we did on the earlier slide. Use the Pythagorean theorem to find the magnitude of the vector. Use the tangent function to find the angle at which it is directed, and that gives you the same answer, and you report it the same way. The resultant is equal to 77.9 at 29.5 degrees north of east, or 29.5 degrees. It doesn't matter to me how you do it. It all depends on your degree of comfort working with trigonometry. It may take you just a hair longer doing it this way, but if you're more comfortable with setting up your expressions off to the side, that's fine. So that's how to use algebra to find the resultant when three or more vectors are present.